How's it going, Internet? I'm Tim Stedman, and welcome to Get Psyched with Tim Stedman. You know, one of the things I love about teaching psychology is that I can take any random thought that pops into my head and easily relate it to whatever I'm talking about in class that day. Kind of like earlier while I was setting up my camera, I was thinking about how funny it is on TV shows when they bleep out all the bad words. Like, it isn't really the fact that these people are saying bad words on TV that I think is funny. It just gives me a good when I hear the noise in quick succession. Hilarious. Anyways, we should probably go ahead and get by getting started with our Unit 1 review. Today, we're getting started with the first unit of AP Psychology, the biological basis. But for the sake of my job security, how about we take a look at the uncensored version of what I said just a few moments ago. Kind of like earlier while I was setting up my camera, I was thinking about how funny it is on TV shows when they bleep out all the bad words. Like, it isn't really the fact that these people are saying bad words on TV that I think is funny. It just gives me a real good chuckle when I hear the loud beep noise in quick succession. Flippin' hilarious. Anyways, we should probably go ahead and get educated by getting started with our Unit 1 review. You know, personally I think the censored version is a bit more entertaining. Just imagine if I did that throughout the entire video. Oh man, that'd be pretty great. Now, if this is your first time tuning in, before watching this video, I highly recommend you checking out the... Alright guys, joke's over, come on. If this is your first time tuning in, before watching this video, I highly recommend you checking out the review videos on the 4 AP Psych science practices. In my grand opinion, and take it for what it's worth, it's a good idea to be comfortable with each of the science practices before learning the course content. You are expected to show an understanding of these practices throughout the entire course, so they are kind of a big deal. Unit 1 is going to look at how our biological structures, such as our brain and nervous system, have a huge influence on our behavior. We're going to get started with our review by taking a look at how our heredity and environment interact with one another in order to influence our behaviors. Which brings us to a psychological tale as old as time, the nature versus nurture debate. Now, nature refers to the genetics we inherit from our parents. These include both physical and psychological traits, while nurture refers to our environmental influences and the experiences that will end up shaping us from when we were little babies all the way up through adulthood. Nature gives us our physical traits like hair color or height, while nurture provides us with the resources needed to shape our behaviors, develop our skills, and influence our personality. And while it is common to view this as a nature versus nurture, it is really more like nature and nurture, as they both are constantly interacting with one another in order to shape our behaviors. Charles Darwin's theory of evolution by natural selection explains how traits that enhance survival and reproductive success are more likely to be passed on to the next generation. Darwin's theory is going to help us understand why certain behaviors, even those that might seem pointless today, have persisted through human history. While evolutionary psychology offers valuable insights, it has also been unfortunately misused, as we have seen with eugenics, a movement aimed at improving the human population through selective breeding. Promoted in the early 20th century, eugenics led to enforced sterilizations and what people thought was justified discrimination, showcasing some of the darker sides of science. And believe it or not, the idea of eugenics was actually pretty strong in the US from the early 1900s to the 1930s. And this serves as just another reminder of the importance of maintaining ethical integrity in applying these various theories, a key component of science practice too. To further unpack the interaction between nature and nurture, psychologists use specific research strategies that isolate the influence of our genes and the environment. Twin studies involve studying identical twins under various conditions. Because of their identical genetic makeup, researchers can conclude that any difference in behavior is probably influenced by the environment. Adoption studies offer another layer of insight by studying the behaviors of children who are raised apart from their biological parents. This allows the psychologist to separate the influences of the home environment from genetic factors. And family studies look at traits across generations within the same family, helping to identify how much a trait might be influenced by inherited genetic factors versus environmental conditions. Now that we've taken a look at the interaction between our genetics and the environment, let's shift gears to understanding the core structure that makes it all possible, the body's primary communicator, the nervous system. The nervous system is going to consist of two main parts: the central nervous system and the peripheral nervous system. The central nervous system, or CNS, contains our brain and spinal cord. The brain acts as the command center, processing incoming sensory data and coordinating responses. Meanwhile, the spinal cord functions as a crucial relay station, organizing and sending neural messages to various parts of the body. The peripheral nervous system, or PNS, oh, I'm immature. I mean, that one should have probably been censored. The peripheral nervous system, or PNS, includes all the nerve endings that branch out from the brain and spinal cord and extend throughout the body, including the organs, arms, and legs. The PNS transmits information to the CNS and also takes orders sent from the CNS. The peripheral nervous system can be broken down further into the somatic and autonomic nervous system. The somatic nervous system is responsible for processing our voluntary movement and transmitting sensory information to the central nervous system. From practicing our dance moves in hopes of becoming a viral sensation to simple acts such as waving goodbye, are all controlled by the somatic nervous system. The autonomic nervous system is responsible for our involuntary functions such as heart rate, digestion, and breathing. Now, I consider the autonomic system the unsung hero of the nervous system, constantly working hard in the background to make sure we maintain normal levels of functioning. The autonomic nervous system can be broken down further into the sympathetic and parasympathetic nervous system. The sympathetic nervous system is responsible for your fight or flight response and activates when there is a perceived threat, while your parasympathetic nervous system brings the body back to normal functioning once the perceived threat is gone. All right, now that we have a basic understanding of the nervous system and its structures, next we're going to take a look at what's happening in the nervous system at the microscopic level. Neurons are going to be our nervous system's primary communication cells. These cells can be found all throughout the nervous system, including our brain, spinal cord, and the nerve endings throughout the body. Powered by electricity, the nearly 86 billion neurons in our bodies are responsible for sending neural messages and making sure this information gets to the right part of the body. It's important to know that neurons don't work alone. Glial cells, which outnumber the neuron 10 to 1, play a critical role in supporting the neuron. Glial cells are responsible for supporting, protecting, and providing nourishment for neurons, as well as cleaning up waste in the nervous system. Understanding the anatomy of a neuron is also important in understanding how neurons are able to communicate important messages throughout the nervous system. Starting at the core of the neuron, we have the nucleus, which is going to contain the neuron's genetic information. You can think of it kind of like the brain of the cell. Surrounding the nucleus, we have our cell body, or soma. The cell body provides structural support for the neuron and processes the nutrients needed to energize the cell. Branching off of the cell body, we have the dendrites, which are responsible for receiving incoming messages from other neurons. The long tail-like structure of the neuron is the axon, which is responsible for sending information to the next neuron. And wrapping around the axon, we have what is called the myelin sheath. The myelin sheath is actually made up of glial cells wrapping around the axon of the neuron. By doing this, the neural messages are able to travel at faster speeds. Our nervous system has 3 different types of neurons, all with specific responsibilities. Sensory neurons located throughout the peripheral nervous system are responsible for collecting information from our various senses and sending this information to the brain. While motor neurons, also located through the peripheral nervous system, are responsible for carrying out motor actions sent from the brain, allowing us to control our muscles and movements. These neurons are also responsible for releasing hormones throughout the body. And finally, we have interneurons. Interneurons outnumber our sensory and motor neurons and are located in the central nervous system. Interneurons are responsible for directing messages throughout the entire nervous system. The reflex arc is going to be a reflexive response that will show us how these 3 neurons work together within our nervous system. Now, to explain the reflex arcs, we are going to get some help from our good buddy Doug. All right, what's up, Doug? So, you ready? All right, so while preparing for dinner, Doug accidentally placed his hand on the hot stove. As soon as his hand touches the stove, he reflexively jerks it away due to the pain. Well, what's happening in Doug's nervous system for this action to occur? As soon as Doug's hand touches the hot stove, he will reflexively move it before even processing the pain. As soon as the extreme heat from the stove makes contact with the skin, the signal of pain then beelines it to the spinal cord, where it is quickly handed off to the interneurons. Interneurons in the spinal cord instantly process these signals as being a pain response and will actually skip going to the brain as a neural message normally would. Instead, these interneurons will send a message directly to the motor neuron located in Doug's hand and arm, causing him to reflexively move his hand from the dangerous stimulus, all without any input from the brain. And how exactly are these neurons able to send messages? Well, I am glad you asked. When a neuron receives stimulation, it fires off an action potential, which is just an electrical charge that is collected by the dendrites and cell body and sent down the axon. To produce an action potential, the neuron must receive enough stimulation for a message to be sent. This is known as the neuron's stimulus threshold. The all or nothing principle states that a neuron can do one of two things: receive enough stimulation for an action potential to occur, or it doesn't receive enough and an action potential does not occur. There's no halfway. Kind of obvious. After a neuron fires a message, it enters a refractory period, which is pretty much when a neuron quickly recharges its batteries. During this time, the neuron is unable to send a message. After the neuron is recharged, it remains at the resting potential, ready to send its next message. When an action potential reaches the axon, the neuron releases chemicals to transmit the message to the next neuron. After the transmission, these chemicals are reabsorbed through a process called reuptake, allowing them to be reused and conserving the body's resources. Now, this process is not always flawless, and when there are issues with our neural transmission, it can lead to issues that can impact our daily lives. Multiple sclerosis and myasthenia gravis are both autoimmune disorders where the white blood cells attack the body's neurons. Among other symptoms, both of these disorders lead to issues with muscle weakness and fatigue, as well as the loss of mobility. As we mentioned earlier, the axon terminal of a neuron contains various chemical messengers. These chemical messengers are called neurotransmitters, and they control virtually every aspect of your life. When neurotransmitters relay messages, they can be either excitatory or inhibitory. Excitatory messages increase brain activity by triggering more action potentials, while inhibitory messages slow down brain activity, preventing further action potentials. Often called the feel-good neurotransmitter, dopamine is crucial for our pleasure and reward systems. It influences mood, attention, and movement, and is often linked to addiction. Now here's where I put my money where my mouth is and show you how just about anything can be related to psychology, including my pointless rambling on censoring language at the start of this video. So dopamine plays a key role in how we experience humor, particularly when there's an element of surprise or expectation. When you hear the your brain's dopamine pathways are activated because there's an expectation of hearing something inappropriate or funny. This release of dopamine contributes to the feeling of amusement as the brain enjoys the process of anticipating and then experiencing something unexpected or out of the ordinary. Being part of the reward system, dopamine influences us to constantly seek out things that give us pleasure. Kind of like me obsessively checking my YouTube subscriber numbers. I'm busy! So, if you want to give me a little dopamine boost, how about you hit that subscribe button? Help me keep riding that dopamine high. It would make me so happy. So happy that my brain would just flood with another neurotransmitter known as serotonin. So serotonin is going to help regulate our mood, appetite, and sleep. A lack of serotonin is usually linked to symptoms of depression. Norepinephrine is going to affect our level of alertness and arousal. This neurotransmitter is very similar to our hormone of adrenaline. And by far one of the most abundant neurotransmitters we have, glutamate is going to be an excitatory neurotransmitter that is critical for normal brain functions as it is heavily involved in regulating our cognitive functions such as learning and memory. Pretty important things. GABA, or gamma-aminobutyric acid, is a major inhibitory neurotransmitter which has the main responsibility of slowing down brain activity by reducing the amount of action potentials occurring. GABA lets your neurons know when it's time to take a break. Our body's natural painkillers are the endorphins. Endorphins help us reduce our response to pain and has been known to induce feelings of pleasure and happiness. Next up we have substance P, or substance pain as I like to call it, which is going to be responsible for regulating, well, you guessed it, pain. When substance P is released, we feel pain, letting us know that something is wrong in our body. And our final neurotransmitter that we will be discussing, acetylcholine, is responsible for stimulating our muscle contractions, and it also plays a role in our attention and memory. When the axon of a neuron sending a message links up with the dendrites of a neuron willing to receive a message, neural transmission can occur. We refer to the neuron that sends the message as the presynaptic neuron, while the neuron that receives the message will be the postsynaptic neuron. Now, it's important to note that the neurons don't actually touch. Instead, they form a tiny fluid-filled gap known as the synapse. The synapse is going to be the direct point of communication between two neurons. Neurotransmitters are generally stored in synaptic vesicles that are at the end of a neuron's axon. When an action potential occurs and the electrical energy reaches synaptic vesicles, it forces the neurotransmitters out of the neuron and into the synapse. Located on the dendrites of the postsynaptic neuron are receptor sites tailored to specific neurotransmitters. When a matching neurotransmitter binds to a receptor, it can either inhibit or excite the neuron. Exciting it triggers an action potential in the postsynaptic neuron, while inhibiting it keeps the neuron in its resting state. Once neural communication is complete, the neurotransmitters are reabsorbed back into their synaptic vesicles in a process we know as reuptake. Now, it's also important to know that neurotransmitters are not the only form of chemical messengers in our body that impact our behavior. Working closely with the nervous system, hormones or chemical messengers in the endocrine system also influence our behavior. The endocrine system, which is responsible for regulating our hormones, is going to be controlled by an area of the brain known as the hypothalamus, and its right-hand gland from the endocrine system, the pituitary gland. Right-hand gland. See what I did there? That's a good one. Adrenaline is a hormone that plays a huge role in our fight or flight response. When released, it rapidly prepares your body to spring into action by increasing your heart rate, blood pressure, and energy supplies. Leptin is released by our fat cells and helps with regulating our energy balance by telling our body when to stop eating, suppressing our appetite. On the reverse end, the hunger hormone, or ghrelin, is released into the stomach to stimulate our appetite. It pretty much serves the opposite purpose of leptin by making us hungry when our body needs more energy. Next up, my favorite hormone, melatonin, which is going to be released by the pineal gland when it starts to get dark outside, helping to prepare us for sleep. In the morning, as the sun starts to rise, melatonin production starts to decrease, preparing us to wake up. And finally, we have oxytocin, sometimes called the love hormone. Oxytocin plays a significant role in social bonding and reproduction. It is released as a result of physical touch and is thought to reduce stress while improving our overall emotional well-being. So we've talked all about how our natural body chemicals can influence our behavior, but what about outside substances? Psychoactive drugs are going to be substances that alter our brain function, resulting in temporary changes in perception, mood, consciousness, and behavior. These drugs work by influencing neurotransmitter activity in the brain, either by working as an agonist and mimicking the effects of natural neurotransmitters, or acting as an antagonist to stop chemicals from binding to a receptor site. We also have reuptake inhibitors that block the process of reuptake to increase the levels of a specific neurotransmitter in the brain. A common reuptake inhibitor, SSRIs, work by blocking the reuptake of serotonin to fight symptoms of depression. Stimulants such as caffeine and cocaine increase brain activity, resulting in elevated levels of alertness, attention, and energy. Depressants like alcohol tend to slow down central nervous system activity, which can lead to decreased anxiety, inhibition, and motor skills. Even a moderate amount of alcohol can affect our cognitive functions and mood. Hallucinogens impact the nervous system, altering perceptions, moods, and thoughts. And believe it or not, marijuana is classified as a hallucinogen. Opioids such as heroin are known for their strong pain-relieving properties and euphoric effects. Opioids from outside substances bind onto our brain's opioid receptors, significantly increasing our dopamine levels, which can lead to severe addiction. Addiction is going to be a chronic condition brought on by repeated drug seeking and use, despite the harmful consequences associated with taking the drug. Addiction impacts several areas of functioning, including physical health, relationships, and school or work life. With continuous drug use, the brain begins to adapt, meaning the original drug dose someone is taking does not produce the same effects as before, and as a result, more of the substance is needed to achieve the same effect, causing the individual taking the drug to build up a tolerance. Withdrawal symptoms are experienced after developing a physical dependence on a substance and then stopping its use. These symptoms, which can be physical or psychological, range from mild to life-threatening, depending on the substance and the duration of use. All right, so we've been talking a lot about how different chemicals or substances impact our brain, but haven't really talked about the actual brain that much. So how about we uncover the mysteries of the brain's structures and functions by taking a quick guided tour of the brain. Starting at the base of the brain, we have the brainstem. The medulla, located at the bottom of the brainstem, is responsible for controlling automatic functions such as breathing, heart rate, and blood pressure. It is essentially the brain's autopilot system. The cerebellum, often referred to as the little brain due to its shape, is located just behind the brainstem and is responsible for our motor control, coordinating voluntary movements such as posture, balance, and even helping with speech. The reticular activating system, or RAS, is a network of neurons starting in the brainstem and branching throughout every corner of the brain, is responsible for regulating our sleep-wake cycle and our attention. Bordering the brainstem, we have the emotional center of the brain, our limbic system. Located primarily in the limbic system, the brain's reward center is going to calculate and respond to rewards, playing a critical role in decision-making and addictive behaviors. The thalamus acts as the brain's sensory relay station, channeling incoming sensory information to the appropriate areas of the brain. Smell is going to be the only sense that is not processed by the thalamus. The hypothalamus is a tiny but powerful area located just below the thalamus. It is responsible for regulating vital life functions such as hunger, thirst, temperature, and emotional responses. Now I want you to listen careful here, because what I'm going to say next is not my words. It comes from a college-level neuroscience textbook. I repeat, not my words, but a very solid tip on how to remember the hypothalamus. So basically, when you think of the hypothalamus, just think of the 4 F's of survival: fighting, fleeing, feeding, and f***ing. All right, literally I said mating. I literally said mating. I'm starting to think that someone's out to get me. As we mentioned earlier, the hypothalamus also controls the pituitary gland, which is considered the master gland of the endocrine system, influencing other glands in the body. It plays a role in regulating growth, metabolism, and reproduction. The primary function of our hippocampus is going to be to create new memories. The hippocampus allows our current thoughts to be saved in our brain so we can retrieve them later on. A small almond-shaped cluster of neurons known as the amygdala is going to play a key role in processing emotional aspects of our memory, as well as our emotional responses, specifically our fear and pleasure responses. Next up, we are moving to the most advanced area of the brain, dealing with all of our complex thoughts and functions, the cerebral cortex. Our cerebral cortex is divided by the left and right hemisphere, with the corpus callosum being the bridge that connects them. The occipital lobe, located at the back of the brain, is primarily responsible for visual processing, interpreting everything that we see. The temporal lobe, conveniently located right above our ears, deals with interpreting auditory information and sounds. The parietal lobe, positioned at the top of the brain, processes sensory signals from various parts of the body, making it crucial for spatial orientation and navigation. And our last lobe, the largest lobe in the brain, our frontal lobe, is responsible for decision-making, problem-solving, planning, and controlling speech and motor movements. Now, located within our lobes are several specialized areas of the brain, all with very specific functions. At the tip of the frontal lobe, the prefrontal cortex is the part of the frontal lobe that is responsible for decision-making, planning, and social behavior. And would you look at that? We can also use the prefrontal cortex to help explain why I think the noises are just so funny. Except, you know, they are starting to get a little less funny when they're being used against me. When I bleeped out the words, your prefrontal cortex was at work, quickly assessing the situation, determining that the words being bleeped out were likely inappropriate. The prefrontal cortex helps regulate our responses and maintain social norms, which is why you found the bleeps amusing. It's your brain recognizing that something is being intentionally censored. Now, this area of the brain is not fully developed until about our mid-20s. Maturing can be seen as a result of our prefrontal cortex developing its ability to better regulate the emotionally charged impulses from the amygdala, leading to more controlled and thoughtful responses as we grow older. Located at the back of the frontal lobe is the motor cortex, which is responsible for our planning and executing of voluntary movements. Just behind the motor cortex, at the front of the parietal lobe, lies the somatosensory cortex. This area processes sensory information from across the body, creating a sensory map that aids our understanding of the physical environment. And if your research on the brain hasn't brought up this horrifying visual yet, well, here you go. Absolutely terrifying. So yeah, that guy represents the areas of the body the somatosensory cortex influences the most. Broca's area, located for most people on the left hemisphere of the frontal lobe, It is responsible for our speech production, helping us form words and sentences more effectively. Another key language area, Wernicke's area, situated in the left hemisphere's temporal lobe, is essential for language comprehension. It's going to process both spoken and written forms, enabling us to understand others when they speak to us. And while we're on the topic of language, let's talk about something called aphasia. So damage to either Broca or Wernicke's area can lead to issues in our ability to produce or understand speech. As we just learned, our brain can have issues of its own, which unfortunately can impact our daily lives. Oftentimes, an overactive corpus callosum that is uncontrollably firing message between the two hemispheres of the brain can cause epileptic seizures to occur. As a result, scientists came up with the split brain procedure, where they cut the corpus callosum, making communication from the left and right hemisphere impossible. Although it may seem to be a bit extreme, the split brain procedure has proven to be highly effective in significantly reducing the frequency of epileptic seizures. Additionally, it has taught us a lot about the distinct specializations of each brain hemisphere. Cortex specialization highlights the distinct functions of different cerebral cortex regions. For example, the left hemisphere primarily manages language tasks such as speech and comprehension, while the right hemisphere excels in spatial reasoning and facial recognition. Now, I'm sure you've heard how the right hemisphere of the brain controls the left side of the body, while the left hemisphere of the brain controls the right side of the body. This is actually true, and we refer to this as contralateral hemispheric organization. And while we don't know its true purpose, scientists have hypothesized that this part of our brain evolution helps our brain in processing sensory information and motor responses in a more efficient way. And while on the topic of brain injuries, it's also important that we understand brain plasticity, which is a pretty cool process where our brain is constantly changing its structure and functions as a result of injury or learning. Functional plasticity is our brain's ability to shift specific functions from a damaged area to a non-damaged area, helping us recover from brain injury. While structural plasticity is the brain's remarkable ability to change its physical structure through learning and experience. The brain is constantly strengthening connections between neurons and creating new pathways in response to our learning. And now to answer the question you are all probably wondering, how do we know all we know about that wrinkled little guy we call the brain? Well, in the later half of the 20th century, we saw the invention of brain scans, which gave us a sneak peek of the inner workings of the brain. The fMRI measures brain activity by detecting changes in blood flow, highlighting areas that consume more oxygen during active mental processes. This technology allows us to identify which brain regions are involved in various cognitive and sensory activities. The EEG utilizes electrodes placed on the scalp to measure the brain's electrical activity. Although it doesn't offer a visual image of the brain, the EEG is invaluable for analyzing the timing of brain responses, enabling researchers to see how quickly the brain reacts to various stimuli and activities. Before these scans were invented, there were still a few ways to study the brain. Lesioning studies occur when an area of the brain, usually an animal, is intentionally damaged in order to observe the damage's effect on behavior. Researchers can then see how this brain lesioning impacts individual behavior and mental processes. Case studies typically involve observing unique cases of individuals with naturally occurring brain damage due to accidents, strokes, or disease. By studying the changes in behaviors and cognitive abilities resulting from the brain damage, researchers can predict the function of the damaged brain area. Now, as we further explore the brain, it is important to understand not just its structures, but also how it controls our level of consciousness. Consciousness refers to our awareness of our own mental processes and the external environment. It's what you're hopefully using right now to listen to me and understand what I'm saying. Consciousness works on a spectrum that is constantly changing. The two levels of consciousness we switch between the most are going to be wakefulness and my favorite pastime, sleep. Our body's sleep-wake cycle is controlled by an internal biological clock known as our circadian rhythm. The circadian rhythm runs roughly on a 24-hour cycle and lets us know when it's time to go to sleep and when it's time to wake up. Unfortunately, the demands of our modern world often throw a wrench into this finely tuned system. Factors like jet lag from traveling across multiple time zones, working night shifts, or just not being able to take your phone away from your face can all disrupt our natural rhythms, leading to sleep disturbances. And once we finally do get some sleep, it may be lights out for us, but not so much for the rest of our body. Sleep comes in multiple stages. We have non-rapid eye movement, or NREM sleep, and rapid eye movement, or REM sleep. Lasting only a few minutes, stage 1 NREM sleep is considered light sleep where we can easily be awakened. our body begins to relax with slow rolling eye movements and reduced muscle activity. During this stage, we may encounter something known as a hypnagogic hallucination, which is just a vivid sensory experience that occur as we drift off to sleep. These hallucinations are often sights or sounds, such as flashing colors or hearing your name called out. After 5 to 10 minutes in stage 1 NREM sleep, we can now transition to stage 2 NREM sleep. This is where brain activity slows a bit further, and it's going to be marked by specific brain waves such as the sleep spindles and K complexes. This stage is still considered light sleep, but waking up becomes a little more difficult. Stage 3 NREM sleep is characterized by slow delta brain waves. This is our deepest sleep where it is much more difficult to be woken up. This final stage of NREM sleep rejuvenates the body, strengthens the immune system, and consolidates our memories. After cycling through the stages of NREM sleep, we enter REM sleep. Often referred to as paradoxical sleep, REM sleep is marked by an increase in brain activity that is very similar to the brain activity we see while we're awake. Now, a nice little fun fact about REM sleep: when we enter this stage of sleep, a process known as sleep paralysis can occur. When this happens, our muscle movements are suppressed, mainly so that we don't act out our dream. This is a completely normal process that keeps us safe as we slumber. However, though, it is actually possible to wake up with sleep paralysis, and this is where our mind is pretty much awake, but our body still thinks it's asleep, and this makes it so we can't move. We can also experience some pretty terrifying hypnagogic hallucinations when this happens. Some UFO abductions have even been disproven just as a case of sleep paralysis. REM sleep plays a crucial role in processing emotions, consolidating memories, and our learning. It's a vital stage of sleep that our brain needs to function effectively while we're awake. If we don't get enough REM sleep, we can experience what is known as REM rebound, where our brain increases the duration of REM sleep to help maintain the balance of our sleep cycles. So as you can see, sleep isn't just a passive state, but it's actually a very active and essential part of our well-being. This can be seen with the restorative theory, which suggests that we sleep because it is important for the physical repair and recovery of our bodies. During sleep, especially NREM3, our body starts to repair body tissues and stimulate muscle growth. This is why we feel rejuvenated and mentally alert after a good night's rest. The adaptive theory is going to explain why we sleep at night. This theory proposes that sleep evolved to enhance our chances of survival. By sleeping, we conserve energy and reduce the risk of encountering danger during our most vulnerable hours, the nighttime. Alright, so if we have theories explaining why we sleep, obviously we are going to have some theories explaining why we dream. The activation synthesis theory states that dreams result from the brain's attempt to make sense of the random neural activity we experience during REM sleep. The brain takes these random signals and arranges them into a story, which we experience as dreams. Meanwhile, the memory consolidation theory suggests that dreams play a critical role in processing and consolidating memories. During REM sleep, the brain sorts through the day's experiences, decides what we're going to keep, and also integrates this information into our long-term memory. So have you ever had a teacher who told you to make sure you get a good night's rest before a test? Well, believe it or not, they weren't wrong. Who would have known? Yeah, teachers can be pretty smart sometimes. Alright, so we talked about the stages of sleep, what happens when we sleep, and why we sleep. But what happens when we don't get enough sleep? Something a whole lot of us can probably relate to. Sleep deprivation not only leaves us feeling exhausted, but also has some serious effects on our health and cognitive functions. Physiologically, sleep deprivation can lead to a weakened immune response, making us more likely to get sick, and an increased heart rate, which over time can strain the heart, leading to an increased risk of heart disease. Psychologically, it often results in impaired memory and a reduced ability to concentrate, as well as increased irritability and mood swings. Sleep deprivation can come from environmental distractions, our phones being a major culprit, but it can also be the result of a sleep disorder. Insomnia involves difficulty falling asleep or staying asleep, even when we have the chance to do so. Insomnia is often caused by stress and poor sleep habits, and treatment generally includes sleep therapy, improving sleep habits, and some form of medication. Narcolepsy is characterized by extreme daytime sleepiness and sudden episodes of falling asleep. Treatments often include medications such as stimulants and antidepressants. REM sleep behavior disorder involves acting out vivid dreams with sudden violent arm and leg movements that can lead to injury during sleep. Treatment typically involves various medications, and in some circumstances, a simple melatonin supplement will do the trick in reducing symptoms. Sleep apnea is caused when blocked airways interrupt breathing during sleep, disrupting REM sleep and reducing overall sleep quality. Common symptoms are going to include snoring and daytime sleepiness. While treatments typically involve lifestyle and dietary changes, some individuals with sleep apnea are given a CPAP machine, and in rare cases they can elect to have surgery. Somnambulism, or more commonly referred to as sleepwalking, involves getting up and walking around during stage 3 NREM sleep. General treatment for this focuses on safety measures to prevent injuries during episodes, such as locking doors and windows, and in more severe cases, medication. Alright, so that wraps up sleep. And for our final topic of Unit 1, and a beefy one at that, we're going to be talking all about our senses. So sensation is going to be the process of our sensory organs collecting information from our body and the environment and sending this information to the brain for processing. When our sensory organs collect this information, a process known as transduction occurs, where the physical stimulus, such as light waves, are converted into electrical signals that the brain can understand. To understand how we are able to detect this information, we have sensory thresholds. The absolute threshold refers to the minimum strength that a stimulus has to have in order to be detected 50% of the time. This threshold represents the point at which we can detect and perceive a stimulus from each of our senses. You can even test this out yourself. Set your TV volume all the way to 0, stand a few feet back, and slowly raise the volume till it gets to the point where you can just barely hear it. That would be your absolute threshold for sound. Now the difference threshold, also known as the just noticeable difference, or JND, is going to be the smallest change in a stimulus that we can detect. Let's say your TV's volume is set to 60% and is increasing incrementally by 1%. The point that you realize that there is a change in volume is going to be your difference threshold. Weber's law states that our ability to detect a change depends on the intensity of the original stimulus. Think about it. It would be much easier to detect a change in volume from 20% to 25% rather than a change from 90 to 95%. We are also going to have sensory adaptation, which is just going to be our brain's ability to decrease its sensitivity to constant stimuli. This response allows us to tune out sensations like the continuous touch of a necklace against our neck or the feeling of our pants against our legs, enabling us to focus on more important changes in our environment that might demand our attention. Another important aspect of sensation, sensory interaction, is the process by which different senses influence and interact with one another in order to enhance our perceptions. A very interesting example being a condition known as synesthesia, where the stimulation of one sensory pathway leads to the automatic and involuntary experience of a secondary sensory pathway. People with synesthesia might see a specific color when they hear certain sounds, or might even experience a specific taste when looking at a certain object. Every one of our senses has a sensory receptor. These receptors are just specialized cells within all of our senses that transduce sensory information to the brain. So how about we take a look at each of our senses in order to see how they work, starting with our sense of vision. When light waves from the environment reach our eyes, through a process known as accommodation, the lenses in our eyes change shape in order to focus our vision. This will direct the light to the back of the eye, projecting a clear image onto the retina, which is where sensory receptors for our vision are located. The light is then concentrated on the fovea, allowing for sharp, detailed vision. And finally, the converted signals are sent through the visual nerve to the brain for visual processing. And a cool little fact about the visual nerve, there are actually no sensory receptors there, which leads to a blind spot in our vision. But luckily this area is rather small, and it's pretty easy for our brain to just fill in the blanks for us. The sensory receptor cells for our vision are the rods and cones. Rods are highly sensitive to light, which helps us see at night, while cones respond to color, allowing us to perceive the wide range of colors that we can. Once light waves reach the retina, the information is processed by the rods and cones. These messages are then filtered through the bipolar cells, then sent to the ganglion cells, which act as our visual nerve, sending the message to the brain. An important aspect of our vision is seeing in color, and we have two major theories that explain how we are able to do so. The trichromatic theory states that we have 3 different types of cones, with each one being sensitive to either red, green, or blue light. According to this theory, the colors we see are a result of the brain processing the different signals that these receptors send when they are stimulated. So if you were looking at something that is purple, both red and blue receptors would activate, allowing our brains to interpret the color accurately. Building on the trichromatic theory, the opponent process theory proposes that color perception involves neurons in the occipital lobe that process colors in opposing pairs of blue-yellow, red-green, and black-white. When one color in the pair is stimulated, the other is inhibited. Now this process is evident when we experience an after image. Stare at the green circle on the screen for a bit and watch what happens when it goes away. If it worked, after the green circle disappears, you should very briefly see an after image of a red circle. This original green circle stimulated the red-green pairing more towards the green side, and then when the stimulus left, there is a momentary rebound effect where we see the opposite color pair. Our sense of sight is a very intricate process, and because of this, sometimes things can go wrong, which can impact our vision. Nearsightedness or myopia occurs when the eye is too long, causing light to focus in front of the retina, leading to blurry vision when looking at faraway objects. Farsightedness or hyperopia occurs when the eye is too short, causing light to focus behind the retina, leading to blurry vision when looking at objects up close. Color blindness is the inability to perceive some or all colors. With dichromatism, there is difficulty distinguishing between two colors, such as red and green, while those with monochromatism are unable to perceive any color at all, only shades of gray. Prosopagnosia, or face blindness, is a neurological disorder impairing the ability to recognize faces. Those with the condition can see individual features, but struggle to perceive the face as a whole. Blind sight is a condition where individuals can respond to visual stimuli without conscious perception. Clinically blind due to brain issues, not eye issues. Those with blind sight still process visual information, but at an unconscious level. So they can't physically see anything, but their brain can interpret everything that their eyes are picking up. They just can't see it. It's very confusing to me sometimes, but it's real. This one actually blows my mind, I'm not gonna lie. All right, so that does it for our vision. Next up, we're gonna take a look at another widely used sense, our hearing. When sound waves enter the ear, they strike the eardrum, causing it to vibrate. These vibrations are then transferred to the auditory ossicles, which are small bones in the middle ear that amplify and relay the sound to the cochlea. Inside the cochlea, sensory receptors for hearing, known as hair cells, move in response to the vibration and converts these sound wave vibrations into neural messages. Pitch is going to refer to how high or low a sound is perceived, depending on the frequency of the sound waves. High frequencies produce higher pitches, while low frequencies produce lower pitches. Amplitude determines how loud a sound is, which is directly related to the energy and intensity of a sound wave. The greater the amplitude, the louder the sound. Sound localization is the ability to determine where a sound is coming from by our brain comparing the differences in timing and intensity of sound waves arriving at each ear in order to pinpoint the location of a sound. And just like how our sense of sight had a few theories explaining some of its processes, the same can be said for our sense of hearing. The frequency theory states that the rate of nerve impulses traveling up the auditory nerve matches the frequency of a tone, allowing us to detect its pitch. The Volley theory extends the frequency theory by suggesting that groups of auditory neurons take turns firing in rapid sequence, allowing us to perceive sounds with frequencies higher than 1,000 hertz, which individual neurons can't keep up with. And the place theory is going to argue that different pitches stimulate different areas on the cochlear's basilar membrane, meaning the location where the membrane vibrates the most allows us to distinguish the pitch of the sound. Our process of hearing can be interrupted, leading to issues with gathering and perceiving sound waves. Conductive hearing loss occurs when there's a blockage or damage in the outer or middle ear that prevents sounds from reaching the inner ear. While not a comfortable feeling, the good news is this type of hearing loss is often corrected. Sensory neural hearing loss results from damage to the inner ear or the auditory nerve itself, often due to aging, noise exposure, or genetic factors. This type of hearing loss is generally permanent, but can be managed with hearing aids or cochlear implants. Now, when you experience both sensory neural and conductive hearing loss together, it's referred to as mixed hearing loss. Now, the next stop on our sensory journey, we're going to take a look at the chemical senses of smell and taste. Our sense of smell, or olfaction, if you want to be fancy, begins when odor molecules from our environment, such as pheromones, bind to our receptor cells responsible for smell, which are located on the olfactory epithelium. Pronounced that one right on the first try, go me. These receptor cells transform the smell into a neural message that gets sent to the olfactory bulb and then relayed to the olfactory cortex of the brain. Now remember, smell is unique among the senses as it skips the thalamus and is processed directly by the olfactory bulb, which is located within our limbic system. Our next chemical sense, and our sense of smell's partner in crime, we have taste. Or, for the science nerds out there, gustation. 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 Yeah, I think gustation's right. When we eat something, the chemicals in the food are broken down by our saliva, and then they get in contact with the taste buds, which are just the receptor cells for taste. The taste buds will then create a neural message for the taste and sends it to the brain, where it's relayed through the thalamus to the gustatory cortex. Our taste buds can detect sweet, sour, salty, bitter, and something called umami. Umami is just a savory taste that comes from foods like cooked meats and other high-protein meals. And more recently, just to make things more difficult for all of us, scientists have identified a new taste called oleogustus. This is just the taste of dietary fats, and it's basically a very bitter taste that is described as quite unpleasant. When it comes to personal taste, we can be categorized as a super taster, medium tasters, or non-tasters. Research has shown that the amount of taste buds we all have is going to vary from person to person, which can influence the type of taster we are. Taste is an interesting sense, as it sort of relies on our smell for us to fully experience flavors. You can prove this yourself just by pinching your nose shut the next time you bite into something. I bet you'll notice a pretty significant difference. Now on to the body senses of touch and pain. So our skin is equipped with sensory receptors that detect stimuli like touch, pressure, temperature, and pain. These receptors convert physical stimuli into neural messages that can travel through the spinal cord, are relayed by the thalamus, and then processed in the somatosensory cortex of the brain. Mechanoreceptors detect touch and pressure. Thermoreceptors gauge temperature, allowing us to distinguish between warm and cold, while nociceptors are responsible for sensing and alerting us of any potential pain or harm coming to the body. So pain is going to be both a physical and psychological experience. And according to the gate control theory, pain signals travel through a gate in the spinal cord that can open and close to regulate our perception of pain. This gate can be influenced by physical and psychological factors, which is why we might not always feel pain immediately during stressful or distracting situations. An intriguing example of how pain has both physical and psychological aspects is the phenomenon of phantom limb sensation, where individuals continue to feel pain or sensations in a limb that has been amputated. This occurs because the brain still receives signals from the nerves that originally served the missing limb, demonstrating how deeply our perceptions and mental state can influence our experience of pain. And to finish up our Unit 1 review on the biological basis of psychology, we have our final two senses, senses that you may not have heard of before but are still very important to our functioning: the kinesthetic and vestibular sense. So our kinesthetic sense detects our body position, weight, and movement of muscles, helping us track the position and movement of our bodies. Proprioceptors located throughout our muscles and joints track body movements, alerting our brain of these movements. Once the neural message reaches the somatosensory cortex, it is processed to give us a clear sense of our body's position and motion, allowing us to move smoothly and coordinate our actions effectively. And our vestibular sense is going to provide our brain with information about balance and spatial organization. Hair cells located in the semicircular canals of the ear react to changes in head movements and orientation, triggering nerve impulses that mainly get sent to the cerebellum, allowing us to maintain and coordinate balance. And that's all she wrote for Unit 1, and man oh man am I worn out. So, if you have any questions about anything mentioned in this video, feel free to drop a comment and I'll see what I can do to help out. With that being said, I will see you all next time for our Unit 2 review on cognition. Peace.